What happened there?
How about now? Why is this thing
I can
echoing?
hear you now.
But now I got lots of echoes. This is weird. Why am I hearing echoes? How about now? Okay. All right. Let me know if you have any issues. Okay. So, let's see. Move this out of the way a little bit. You'll need this, I guess. Okay. So we're gonna review the number systems. Um, exit this mode. Okay, let me try to make this a little more comfortable. Okay. These are the number systems that we talked about, right? The binary, octal, decimal, and the hexadecimal. Decimal is a base 10 counting system, right? It's what we learn at school. That is what we use every day, right? Every day we count stuff by 10. But in computers, we have binary number system and octal and hexadecimal. Okay? And these are the digits. We talked about these, right? The digits that these systems use, right? In binary, we have only 2 digits, 0 and 1, right? That's like the light switch, right? When you have the lights turned on, we say it's 1, and if we turn it off, we say it's 0. And that matches how digital circuits work inside computers, right? All the digital circuitry, that's how they work. And sometimes we do call those switch circuits, you know. And also we have the octal system, right? Counting by 8. we go from 0 to 7, and then we do a carryover, and that becomes 1 0, right? In base 8 counting. And then hexadecimal is we count by 16, right? And we have 16 digits from 0 to 15, 0. And when we get to 10, we use the letters for digits, right? So these are conversion tables between binary and octal and hexadecimal, right? These things you should remember. Once you remember, really, it would make sense when I say 5. You tell me it's 101, right, in binary, or 0101. That's in 4 binary digits, right? If we say 9, what is it? It's 1001, right? As you can tell, you can remember these relatively easily, right? 0 is 0, and 2 is 10, 4 is 100, 8 is 1000, right? And then 16 is 100000, right? 1 with 4 0 digits. That's 16. And that is, you know, every time you have one more zeros, if I put some notes down here, right? If I write it down here, we can tell, you know, 0 is 0, right? And then 1 is 1, and 2 is 10, right? 4 is 100, and 8 is 1000, right? Every time you add a 0, the number in decimal doubles, right? And then 16 is 1, 2, 3, 4 zeros, right? So every time you add a 0 in binary, the number basically doubles, right? And also this makes it a little easier to remember the others, right? So if 2 is 10, 3 would be what? Anyone of you? 3 is
101.
no, 3 is 2 at 1 at 1. Right? 2 plus 1 is 3, right? In decimal. So 1 0, and then you add 1 to it.
So it's 10. 4.
So it's 1 1, right? In binary it would be 1 1. Does that make sense? So when it's 1 0, 0 plus 1 is 1, right? So when we do binary addition, let me see if we have it's okay. These are the facts that you need to remember. But before we get there, let me add a okay. Let me add a page to do some binary. Okay. This is what, let's say 0 plus 0 is what?
0.
0, right? That's easy. And 0 plus 1
1.
is 1, right? Easy, right? And also 1 plus 0, 1, right? And in binary, remember we're doing binary, right? 1 plus 1 is not 10. You can't say it's 10, right? 10 is decimal. It's 1 0, right? Because I mean, there's no good way to read this number. So because it's binary, we'll just call it 1 0, right? And this is, if we convert this to decimal, this would be 2, right? Because 1 plus 1 in decimal is 2, right? But in binary counting, in binary number system, we don't have other digits. We only have 0 and 1, right? So whenever you do 1 plus 1, it becomes 0, and then you carry 1 over, right? You carry 1 to the next digit position, right? So that becomes 1 0. And now, if we do 1 0 plus 1, what do we get? 1 1, right?
11.
Because 0, because this is basically the same as, right? 1 0 plus 0 1. And if you line these up, right, it would be 1 0 and 0 1, right? Right? And then you do the addition here, digit by digit. 0 plus 1 is 1, right? And then 1 plus 0 is also 1, right? Now, the thing is, what if we do 1 1 plus 1 more? Now what do we get?
Don't you get like 1 0 0?
Exactly. Why? Because when we add this one to this one, it becomes 1 0, right? It becomes a 0, and then we carry 1 over to the next digit, right? And when that 1 gets put onto the next digit, now the second position becomes also 1 plus 1, right? And then 1 plus 1 is again 0, and then 1 carries over, right?
And so on.
That's this one, right? That's this third one. So, and if you convert this, if we convert all these to decimal, remember this is binary we're talking about, right? So if we do decimal, this would be 0 plus 0. In decimal, that's still 0, right? That doesn't change. And 0 plus 1 is still 1, right?
Only
And
1 plus 1.
1 plus 0 is still 1, right? However, in decimal, we do 1 plus 1,
Which is 2.
we got 2.
Same thing for
Right?
also 1 hexadecimal.
Exactly. And in decimal, 1 0 is 2, right? So this is basically 2 plus 1, right? In decimal, we have 3. So we do this, we do 3, right? And as we see here, decimal 3 is binary 1 1, right? So this is essentially the same as 3 plus 1. And in decimal, we have 4, right? Or in octal, it would work the same way as you just said, right?
Mhm.
And in hexadecimal, it works the same way.
But whenever you hit like 8, it works differently for octal.
Exactly.
And whenever you hit
When you have a octal counting system, when you count to 7, you run out of digits, right?
then you go back to
And so the next thing becomes 1 0, right? In octal.
And for hexadecimal, it should be F then it becomes 1 0.
exactly. And that 10 is actually 16 in decimal, right?
Because like every number
Yep.
is like 11 total.
Yep. So this is how these number systems work, right? When you do count, when you do, incremental count. What is this? Transcript. Okay. So when you do these counts, and you can still, think about them in terms of decimal, right? In terms of decimal operations, but in those other counting number systems, you only have so many digits, right? You are limited by the digits. So, you I like that. Okay, so whenever you count to the limit,
It
you
starts
do the
over at
carryover.
1 0. It starts over at 1 0 and 1 0 0.
Yep.
1 0 0.
Yeah.
So on.
Exactly. So if you look at this 100, and if we go back to the conversion table we talked about earlier, you can see the same thing here, right? 4 is 100, right? In octal. And in hexadecimal, 4 is also 100, right? Because the leading zeros, I mean, if you don't have any more digits to the left, then those leading zeros doesn't matter, right? They don't matter, right? In any number system, yeah.
You have like F, like after F is 1 0, like 100,000.
Why is it 100,000?
No, I mean 10,000 after F.
No, after F in hexadecimal system, it would be 10, right?
Yeah, it's 1 0 and binary, like 10,000.
It's not 10,000. It's 1000, right? It's 1 plus 4 zeros. Yeah.
Can you use the left one?
Sure. No.
Well, 1 plus 4 zeros is 10,000.
Yeah, it's written in the same format as 10,000. Like, but when you say 10,000, that usually, it sounds to anybody, it would be in decimal system, right?
So you have to make
So-
it look like it's not in decimal system.
Yeah. So, no, these are the facts that I would encourage you guys to remember. I mean, the digits is fine, right? You can remember those. The decimal values of each hex digit. I mean, from 0 to 9, they're the same, but from A to F, you gotta remember those, right? A is 10, B is 11, to F, which is 15. Yeah, these two, the binary values of each of those, that's the conversion table that we just talked about earlier. And again, this is the way you convert a decimal number. The decimal number here is 97,425, right? And when you need to convert that into binary, you basically do division by 2, right?
So you basically do division by 2 and from 0 0 0 0 0 0 and then the last 0 can be the remainder by 2 and then you keep on doing it until it's like 1.
Yeah. Till you run out, right? Till you can't do any more division, right? So anytime you divide by 2, either this number can be fully divided then you get a remainder of 0, right? Otherwise, you get a remainder of 1.
And then why is there a B? It says like, if it can't be a B. Why is it text?
This is the way that we note that this is a binary number,
B
right?
stands for binary.
No, this means in computer language, that means this number is a binary number. Because this is also a valid decimal number, right?
Mm-hmm.
Because if this is decimal, then it's a big number, it's huge, right? But if it's a binary number, how do we know that, how do we tell the computer that this is a binary number? Right? This is what we use to indicate that this is a binary number. So we say 0B. And what we do here, oh, I didn't put that in the review, but last time, okay, and when we do octal, right, we say 0O. That indicates the number following is an octal number. Again, because this 276221, that is also a valid decimal number, right? If you don't, identify that clearly. So this binary number converts to this octal number. And again, this is that binary to octal conversion table, right here. So how do we do this conversion? Right?
Can you like break it into like 3 numbers? Because like octal is like 3 numbers, 000.
Yeah.
So then every 3 numbers and convert it back into
Every 3 bits.
like 3 bits.
We call them bits. Right? In binary, because in binary we have numbers, we have digits that are 0 or 1, right?
Mm-hmm.
It's only got 2 digits. So in binary, we also call them bits. Right? Each bit could be either 0 or 1, right? So every 3 bits make up an octal number, right? So that is you can see that from this conversion table, and also you can infer that from the fact that 8 is 2 to the power of 3, right? So 2 to the power of 3 means that 8, the 3 bits can make up 8 digits, right? That's exactly what we need in octal count, the octal number system, right? There are 8 digits, which is from 0 to 7, right? From 0 to 7. And you can see what these 3 bits are.
Is it always equal 8 digits or is it up to 8 digits?
3 digits.
Like, 2 to the power, so you're saying that 3 bits can be
Oh.
up to 8? Or
Yeah, 3 bits. 3 bits can make up numbers up to 8, right? Well, less than 8, actually, 8 digits, but it's up to 8. Well, what is the right word? Up to 8, I guess. From 0 to 7, right? So 0 is 000, 1 is 001, right? 2 is 010, and 3 is 011. All these are facts that we just, need to remember. The way to, help you remember these is also, you can just go from 0 and then add 1 to it every time, right? So 0 is 0, and 1 is, you add 1 to that, right? 2 is you add 1 to that. So it shouldn't be that, difficult to remember, okay, but you do need to remember. And this is also to show us that sometimes it's easier to convert from binary, right? I mean, you can do this conversion directly from this number to octal, right? What you need to do is you divide this number by 8, right? By 8, you also get these remainders, and then you can convert that decimal number to octal. But if we know how to do binary, right, then we can easily convert that to the octal as well, because once we get the binary number, we can just segment this binary number by 3 bits at a time, right? Into 3-bit segments.
What happens if like the number isn't in 3 bits? It goes from being 3 bits. Like if there's like 13, 13.
Well, when you divide a number by 8, your remainders would also be less than 8, right? It would be from 0 to 7, right? And that's what you get in these positions, right? We can, we'll show you how to do that manually in a little bit. But in the content, in the ACSL competition, there are a lot of questions for you to compare numbers, converting between octal and hexadecimal, for example. I mean, the easier way to do that is actually to do it like this, right? If you have this octal number, and if we need to convert that into hexadecimal number, it would be much easier to convert this to binary, right? Because we have this conversion table here. That makes sense? We can convert that into binary, and then then we can re-segment this number by every 4 digits, right? And then we can convert that into hexadecimal. This is also, right? This is the same number as we have above, right? This is the same decimal number, and that converted into the binary number. So if we have a question to convert this octal number 276221 into hexadecimal, right? The easier way would be to convert this into binary, right? With this conversion table. And then you can segment that number, same binary number, into 4-bit segments. And then you use this conversion table to convert it into hexadecimal number, which is 17C91, quite easily, right? Also here, 0x is the marker for hexadecimal numbers in computers. Okay. And so these are ways for us to do these kind of conversions, and we'll do some exercise in a little bit later. Okay, and now if we want to convert from binary back into decimal, how do we do that? We just take these ones, right? The zeros you basically could, for completeness, I wrote them down here, right? So starting from the last bit, which is position 0, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 11, 12, this is 16, right? So let's say if we go from the last digit, which is a 1, right? The lowest digit is a 1, which is 1 times 2 to the 0, right? And the next position is 0, right? That's this 0, 0, 0. All these could be ignored, right? We could do that. But for completeness, I just wrote them all down, so just that we don't, miss anything. And then in here we, do this. That's 2 to the power of 16, which is 65,536 in decimal, right? Plus this is 0, right? This is 2 to the 14 and 13, 12, and so on and so forth, right? And then we add all these numbers together, and then we get 97,425 again in decimal. Okay, this is how you convert back from, from binary back to decimal, right? And if we need to convert from, hexadecimal to decimal, we do the same thing. But now each digit here, we need to do the base 16 math, right? So each digit is a power to the 16, is a base 16 number, right? Yeah.
Is that because is it a base 16 because we have like 16, 3, 1, 0? Like in binary, it's just 1, 2, 1, 0, and octal 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, and then perhaps that's why we need like 16 base to make 1, 0. So it's power of 16.
Yeah. Well, in hexadecimal, basically every position, every digit position in here is the next level of power 16, right? So this is power 16 to the power of 0, right? For the lowest position. And the next one is 16 to the power of 1, right? And this is 2, this is 3, and this is 4, right? So that is 1 times 16 to the power of 4, and then 7 times 16 to the power of 3. And C in decimal is 12, right? To the power of 16 to the power of 2, and then 9 times 16 to the power of 1. And so we do the calculation here, and then add them back together. We got the same number, right? 97,425. This is how you convert, backwards, right? And when we do this from decimal converting to hexadecimal, we do division by 16. Remember? Right? We do division by 16, and then we get the remainder. The remainders would be from 0 to 15, right? Just, you can, if it's more than 16, then you can still, divide that by 16, right? And then you get a smaller remainder. And the remainder is always going to be less than the base, right? The base here is 16. That's hexadecimal numbering system space. And so the remainder is always going to be from 0 to 15, right? And okay, there's the resource on the ACSL's website. So here, let me So let's do an exercise, okay? This is an octal number, 246.
We can't see your screen. You didn't share your screen.
Sorry, what?
You didn't share your screen.
Oh, share my screen, sorry. What is going on here? Hold on. Okay. You see the screen now?
Yeah.
Okay, good. So the exercise is to convert this number from octal to hexadecimal. The number is 246. Okay, with the review we just did, convert this number to hexadecimal number. Let's start now. We got 5 minutes to do this. You done?
No, it's about what's the correlation between octal and hexadecimal?
If you don't know, you can write it down on your sheet. Try to,
I do.
um, you know, what I would suggest you do is you can write it on the sheet, right? When you're working on the problem. This is what I would do, right? Grab one here. If I don't remember, right, then I'll just say 0, 1, 2, 3, 4, 5, 6, 7, 8. Let's just do it. That would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Right? You can just do this when you're working on the problem, right? You can just, lay out the table and then,
Until I get to 246.
no, all you need to do is single digits, right?
I already have a table, but we can do the table. What finally to have some writing with octal girl, octal. So
Yeah, so now what you have 5 minutes to think about this, and then we'll reveal what we do with this, right? Whenever you're done, anybody, if you're done, you can chat with me individually in the chat window and give me the answer. Okay, the solution. If you have the solution. Okay, good. I see Ryan's got it done. All right, time out. So this is octal, right? As we write in computer language, we call it 00246. And each octal digit can be mapped into 3 binary bits. Remember the conversion table, right? So if you don't know how to convert, you can just write it down. I mean, just write the full table out on a sheet, right? Then you can just look at this, right? Once you get that, 6 maps to 110, right? You like if you have that table, or if you remember in your head, you would know that 6 is 110, right? And 4 is 100, right? And then 2 is 010. Okay, right? This is easy, right? I mean, just write down the 3 binary digits for every octal number, for every octal digit. Does this make sense? Okay, does this make sense to you? Remember that table, right? If we go back to that table, because I have to run this slide. I should have another window that has this table in there. But if you don't, then you can always take a sheet, right, and write it down, right? What you need for octal number, what you need is write down from 0 to 7, right? How 0 to 7 maps to binary, right? If I have a digit here that's 247, then the 7 maps to 111, right? Remember I said earlier, those are the facts that you have to remember, right? And if you don't remember, it's not that hard, right? You can write it down. 0 is 0, 1 is 001, right? 2 is, 010, right? You can always do the, incremental calculation, right? And to map out, to write out the whole map, right? For octal numbers and for hexadecimal numbers too, because we need that in the next step. And so once you write this down, so we have how many bits? 9 bits here, right? Right? And then if you look at the coloring that I have here, and basically when we convert when we need to convert to hexadecimal, we just need to resegment this number, right? By every 4 bits. So this is the same number as this, right? These two numbers are exactly the same, right? Because all the digits are the same, right? 0, 1, 1, 0, 0, 1, 1, 0, right? And then 0, 1, 0, 1, 0, 1, 0, 1, right? Going from the lowest to the highest digits, right? So this is still binary, right? All these are binary, right? Now, you see that I have 4 digits, right? That is basically your binary for the hexadecimal numbers, right? Remember, hexadecimal numbers, every digit is 4 bits, right? So if you have that map written out on a sheet, then you can see 1010 maps to A, right? And 0110 maps to 6. Does that make sense now?
Yeah.
So you got, this is a real contest problem, right? From 2001, 2002. And so when you're converting between these number systems, octal, binary, and hexadecimal, remember those 2 maps, right? That's all you need to do the conversion, right? You don't need to do the divisions and multiplications, right? As we, because otherwise you would have to, how otherwise you convert from octal to hexadecimal directly? We don't have a good way to do that. You probably will need to convert this to decimal, right? From octal to decimal, and then from decimal to hexadecimal. That's the only, thing that I can wrap my head about, to manually do the conversions manually. Of course, computers can do these because we have programs written for these kind of things. But actually, inside computers, every number is also stored as binary, right? Remember, computers only know how to do binary. So everything when humans can type different numbers into computers, but once those numbers get inside computers, they're stored as binaries, right? And then computers will do all these kind of addition, subtraction, multiplication, and whatever in binary, right? And then when it gets to present these results to humans, that's when it gets converted back to decimal for you. Of course, this is computer science competition, so they want you guys to know how these conversions are done, right? So how do we verify these results are correct, right? And if we want to, easily understand or verify that these conversions are correct, I would suggest that we basically convert these numbers into decimal, right? So to convert that 246 in octal to decimal, this is how we do it, right? 2 times 8 to the power of 2, and then 4 times 8 to the power of 1, and 6 times 8 to the power of 0. And then that's what we get, right? 166 in decimal. This is that number, right? Same number. And here, when we convert hexadecimal to decimal, we do the, 16 base counts, right? And so A is 10. And 10 times 16 is 160 plus 6. Then we get the same decimal number. Right? But in converting this to hexadecimal, it's much easier to use this conversion, right? Converting to binary, to use binary as the intermediate step. Does that make sense? No? I don't want to lose you. So if anybody has, yep. Okay, I see, two of you got the conversion right. I hope everybody else, understand how this is done, right? And this is what I think the easier way to, do this octal to hexadecimal conversion. And this is another problem that that is a little more complex. So I just did it here. So this question asks you to resolve this expression, this addition, right? So this is two hexadecimal numbers. You have to add them together. Right? To do that, basically, to do this directly, right? Directly with hexadecimal numbers, I think you would basically have to do this. If on the remote, on Zoom remote, if you guys look at the right side of this page here, what I've done there is basically do the hexadecimal digit additions, right? But actually convert them to decimal, right? Because it's really, I don't have the system in my head. Let's say A plus B in hexadecimal is what? I mean, I don't have that in my head. So what I do is I convert them, I do the result, right? I basically convert them into hexadecimal. So 8 is 8, right? Hexadecimal 8 is decimal 8. And C is what? 12, right? C is A, B, C, right? A is 10, B is 11, C is 12. So 12 plus 8 is 20, right? 20 in decimal, right? But then I have to convert that back into hexadecimal, right? So convert back to hexadecimal, 20 is 4, I almost said 14, but it's 1/4, right? It's 1/4 in hexadecimal. So now what I do is I write this 4 down here in the first digit, in the lowest digit position, right? And then I put 1 over to the next position, right? So this 1 is added to the next position, right? So the next position was 5 plus B. And with that carry over, so it becomes 1 plus 5 plus B. Right? This is like how you do, decimal, but now we're talking about hexadecimal. So, and that result becomes 17 in decimal, right? Because I don't have this 1 in my head directly. 1 plus 5 plus B is 1. I don't have that. But, in the end, that's the result, right? That's the hexadecimal result of 1 plus 5 plus B, right? And so I write that 1 down here, right? The second position, and the the one here in the second position here is carried over to the next digit, right? Hexadecimal. So the next digit becomes 1 plus 3 plus 8, which is 12. 12 is C, right? So we don't have a carryover at this position, so it's C right here, right? So the next position is A plus E. A plus E, again, I don't have that in my head, but it is 24 in decimal, right? A is 10, right? E is 14, right? So these values, you guys really need to just know them by head, by heart, right? If I say E, you should be able to say 14 immediately, almost. Right? When I say B, 11, good. Right? So it's not, there are not that many of them, but A plus E, you probably don't know what it is exactly, right?
14 plus 10 is 24.
In decimal, it's 24, right? But 24 is 16 plus 8, right? So that becomes 1/8 in hexadecimal. So to do this addition of to hexadecimal numbers, you basically have to do this, conversion back and forth all the time, right? In hexadecimal, between hexadecimal and decimal, right? Between, base 16 and base 10. You have to do this conversion back and forth all the time, right? This is what I'm saying, right? You have to, do the addition and then get the result, in base 10 numbers, right? In decimal numbers, and then you convert them back to hexadecimal numbers. And then you continue, right? Right? Anybody has any questions from the remote site? Okay, so I'm again showing you a way to do this in binary. Okay, and I think it's easier. It's just that you have to, be careful with this hexadecimal to binary conversion. Okay, so these are the numbers, right? These are the two numbers, exact two numbers. What I do here is convert that into binary. Okay, 8 is 1000, right? 5 is 0101, right? So every hexadecimal number here becomes 4 bits in binary. Remember that conversion table? Exactly, that's what we're talking about again, right? So every one of these hexadecimal numbers become 4 bits over here, right? And now, once we get that done here, we'll do binary additions, right? So in binary, 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, right? It's easy. But now 1 plus 1 is 10, right? So we write the 0 down and put 1 to the next digit, right? So these are carryovers, and up to here we don't have any carryover, right? 0, 0, 0 is 0, 0, 0 is 0, 0, 1 is 1. There's nothing to carry over. But once we encounter 1 plus 1, it becomes 0 and 1 on the next position, right? So we put 1 over here. Now we got 1 plus 1 plus 1. What is that?
1 plus 1 plus 1.
That's 3
That's 3, which is 11.
in decimal, right? Which is 1, 1 in binary. So we write 1 down here and put 1 over to the next digit, right? Carry 1 over to the next digit. Again, we write it up here.
1 plus 1 is 1, 0.
So now 1 plus 0 plus 1 is 0, and again, 1 carryover, right? So we do this. And now we got, I mean, this is binary. Binary is much easier, right? You only have, 4 different possibilities, right? 0, 0, 0, 1, 1, 0, 1, 1, right? 4 possibilities. So once you do all these, and this is the result in binary, right?
Then you convert it back.
Then you convert it back into
And
hexadecimal.
you get your answer.
Every 4 digits, every 4 bits becomes a hexadecimal number, right? So this becomes a little easier than that, right? Here you have to do this constant conversion between decimal and hexadecimal. And here you need to convert them once, and then back 4 times, basically, right? Or 3 times, actually. And then in the middle, when you do the addition, it's all binary. Right? So to me, this method is much easier. I don't know if you guys agree, or, you can pick your own methods of doing these kind of addition or subtractions, right? But I'm just showing you that these are ways that you can work with and, help you get the solutions faster, right? Remember when you do these in competitions, and that's how much you have, right? That's, I mean, you have 30 minutes to do 5 questions, I think. So any questions here? All right, and if you don't have, we have some problems from 2016. Where's my can I make this okay, so let's try to work on these problems. We have 15 minutes to go. Work on these problems. We should be able to, finish at least 2. Okay, let's do first 2 problems. That's on the screen here. Let me see if I could. I'll So there is there are the conversion tables if you need those. Okay. Okay. Mhm. Want to continue to the second one?
Which one's correct?
Um, let me do that myself.
Mhm.
Okay, anybody all done?
First answer.
Hmm.
Is it the first one?
Um, yeah. Okay, so let's do that together on this side. Let me try moving this away here. Let's do that here, right? So the first one is A6, A6, C2E, right? That's the hexadecimal number. Let me make this a little bigger. Right, what this is, so let's make that into binary, right? That would be 1010, right? That's A.
0110.
0110, that's 6, right? 1100, that's C. 0010, that's 2, and 1110, that's E, right? That's binary. And oops. Only, we need to convert that into what? Octal, right? So we need to resegment that number into every 3, right? So let's just do that from the last position would be 110, right? 1110, right? But that's this part. But I'm going to segment that into 3 bits, right? So the next 3 bits is what? 101, right? 101 in here. And the next one, oh, let me just copy that down. So to make it a little easier to work with. Right? If I copy that down exactly, that becomes this. And now I can just move this here and do that every 3, every 3 bits, right? Every 3 bits. Right? Basically, we got the octal number, right? So that is what? 10 is 10 is what? In binary is 2, right? So this is 2, and this is 100 is 4, right? And the next one is 110 is 6, and the next one is 110 again is 6, and 000 is 0, and the next one 101 is 5, and the next one 110 is 6, right? There is our octal number 2466056, right? So that's how you do hexadecimal to octal conversion, right? That's the octal number. And the next one we do the same thing. So 375 is 011, 7 is 111, right? And 5 is 01, hold on, 101, right? That's 5 in binary. That's 375, right? That's what it equals to in binary. And now we can just remove the space in between, so it becomes a little easier to compare. Next, now is hexadecimal 100, right? I shouldn't say that. It's not 100, it's 100, right? It's 1, and then but 4 digits, right? From hexadecimal, so it's 0000 and 0000, right? That's that in binary. Now we remove the spaces or commas in there, right? So now the next one is 1 1. Let's just do it directly because it's binary, right? It's 1 1 1 1 1 1 0, right? That's what it is, right? 7 digits. And now 255 is hexadecimal, and that is actually 1 1 1 1 1 1 1 1 in binary. So if you look at these 4 numbers now all in binary, which one is the longest? The longest is the biggest, right? Is that right? Huh? Yeah. So the second one, this hexadecimal 0x, this 100 in hexadecimal is the largest, right? Right. So when you convert that all into binary, then you can just compare how many bits each one has, one number has, right? So the longest is this one, and that's the largest number, right? So as you can see that this binary conversion is really important, right? And you got to know how to convert decimal into binary. So we can do this one here. 255 is 8 digits of 8 ones, right? We're all done today.
Okay,
So-
thank you.
I'll stop. See you guys on the remote side. Let me see what we'll do next time. Next time we'll do the expression notations, the infix, prefix, and postfix expressions. There's some stuff on the wiki site on the ACSL.org website. So if you guys want to review that, preview that, you can do that at home. But if not, we'll do that next class. Right?
Yes, thank you.
Thank you. Have a nice weekend.
Thank you. Bye.
You guys have a nice weekend.
Bye. Bye. Thank you.
Good weekend.
All right.